having defined the concept of family of directions, let us go and count the number of members of a family. There are important directions like the 100, the 110 and the 111, which are important directions, and we will be dealing with them often when we talk about various properties of crystals, and make a counting of all the members of the family. So, this is for a cubic lattice that we are doing, the simplest of the possibilities. So, if we have the 100 family, you have 1, 2, 3, 4, 5, 6 members of the family, essentially which can be thought of 3 members and their negatives. Therefore, we have 3 into 2, 6 members belonging to this family. As far as the 110 goes, I can of course write 110, I can make one of these things a negative, I can make the other index negative, and I can permute all the ways. I can put the 0 in the first place, the second place, or the third place, and therefore, if I count the positive directions and their opposites, I can have 6 into 2, there are 12 members of the 110 family. The 111 family, which is also a very important family, especially with regard to cubic crystals, and especially face centered cubic crystals, which we call the cubic closed pack crystals, we see that there are 8 members to this family, which can be understood as 4 into 2, 8. Okay. So, these numbers are very, very important, and when we talk about especially something known as the multiplicity factor, with regard to planes, we need to know the number of such planes, and therefore, we need to have a counting of all equivalent possibilities. Now, sometimes in literature, there are alternate symbols to describe directions, for instance, the family of directions, and this symbol of a double square bracket is also used, which essentially is similar to the caret brackets we have been using so far. Now, let us go to the concept of Miller indices for planes. The concept of Miller indices for planes is not as straightforward as the concept of Miller indices for directions, and we need to pay a little care and attention in understanding the concept. In other words, whenever a Miller indices for a plane is presented to us, we have to understand that a certain procedure has been followed in arriving at those indices, and we have to be careful in understanding them. So, let us take one arbitrary plane, and of course, this is a specific plane which passes through 3 points A, B and C in, for instance, a cubic system, of course, a cubic lattice in this case. Now, the A point has vertices 2, 0, 0, B point has 0, 3, 0, and the C has 0, 0, 1 as its vertices. I want to find the Miller indices for this plane. So, first thing I write down the intercepts along the axis, which is nothing but 2, 3 and 1. The next thing, I take the reciprocal of these numbers, and this is where the fact that Miller indices for planes become contra-intuitive, or they are not as intuitive as the Miller indices for directions, and that is why, as I mentioned, you have to take special care in understanding them. So, the reciprocal would be half, 1/3 and 1. I will convert them into smallest integers, that means I will multiply this entire thing by a factor of 6. So, this is nothing but 6 times 3, 2, 6. So, 6 by 2 is 3 and 6 by 3 is 2, and I have got 6. What I will do next is enclose them in the normal brackets as 3, 2, 6. I will not use commas in normal cases between these indices, and wherever I may have a high order index, like suppose I had 13, 2, 6, then I would leave a space to make sure that the 13 and the 2 and the 6 are distinct. So, let me go through the procedure again. I find the intercepts A, B and C along the 3 axes. I take the reciprocal of these indices, and then I convert them to the smallest integers, and finally, I enclose them in brackets. So, for this plane, which is marked in green here, the indices would be 3, 2, 6, and as before, when I am writing an index like 3, 2, 6, I mean the complete set of planes which are equivalent to this plane, which are parallel set of planes. So, even though I mention only a single plane, except when I want to be explicit about a particular plane, I know the indices 3 to 6 refers to the whole set of parallel planes which have this kind of a property of passing through or this kind of an orientation in space. Now, normally when you show a plane, you do not show the entire plane, you only show the part of the plane which lies within the unit cell, which has been marked in this light shaded green. So, that is the part which is shown in usual diagrams, and we have to remember these planes are actually infinite planes, and they therefore pervade entire 2-dimensional space or pass through entire 3-dimensional space. So, like before, we could have the concept of family of planes, and since we have defined the family meaning that they are a translationally equivalent set. Therefore, I just apply the symmetry operations to a given plane, I get all the to be more precise, symmetry related set. Therefore, I need to apply all the symmetry operations on this plane, and I would get the symmetrically equivalent set of planes, which would be called a family of planes. So, this is no different in that sense from the symmetrically related set of directions. And now let me consider the important planes in a cubic lattice. So, there are three important planes: the plane which is shown in orange, the plane which is shown in green, and the plane which is shown in brown. Now, as before, I take the intercepts of this plane along the three axes, and the intercepts will be 1, infinity, infinity. The intercept I do not write as 0, but I translate it by 1 unit. That means, even though the orange plane is actually passing through 0, I do not write it as 0, infinity, infinity. I take an translationally equivalent set, which is this gray plane, and write it as 1, infinity, infinity. The reason for doing this translationally equivalent set will become obvious when I do the next step, which is the reciprocal. So, reciprocal of this would become 1, 0, 0, and then I enclose it in brackets, and that becomes the Miller indices for the plane. And if I want to write the family, I will write it as 1, 0, 0 within a different kind of bracket now, which is the kind of curly bracket which is meant for planes. Now, a few important things here. Number one is that if I had started off with 0, infinity, infinity, and I had taken the reciprocal, then I would again land up with infinity, 0, 0. So, I do not want to do this, and that is why I do not choose this orange plane, but I choose this gray plane, assuming that this is my origin. The origin is situated somewhere here. I choose then this point as 1, 0, 0 as my passing through the gray plane, and then I find out the Miller indices. Now, also this example makes it obvious that why do I take the reciprocal? The reciprocal is to avoid these infinities. The moment I take reciprocals, all the infinities in the intercepts vanish, and therefore, I get a neat number like 1, 0, 0. Now, let me do the same process again for the green plane, which is shown here, which is another important low index plane in cubic crystals and cubic lattices. So, the intercepts for this plane would be, assuming this is my origin, would be 1, 1 and infinity in the third direction. So, it never intercepts the z axis. So, my intercepts are 1, 1, infinity, then I take my reciprocal, which will make it 1, 1, 0, and then enclose it in the bracket for the plane. So, it makes it 1, 1, 0 is my indices for this plane, which is shown in green. The family of planes I would represent within these kind of brackets as 1, 1, 0, and the number of members of this family is 6, while the number of members of the 1, 0, 0 family was 3. Now, I take another, and let me after showing these three examples, I will show the same thing using actually physical models. So, it becomes amply clear where are these planes located. Now, if I take another kind of plane and try to generate its Miller indices, so this is the plane shown in brown, and as usual my origin is located here. The intercepts for this plane are 1, 0, 0 along the x axis, 0, 1, 0 along the y axis, and 0, 0, 1 along the z axis. So, my intercepts are 1, 1, 1, the reciprocal of intercepts will be 1, 1, 1, and therefore, I will put these kind of brackets to show that it is a set of planes and the Miller indices for it. The family of planes will be shown by these brackets, it is 1, 1, 1, and there are 8 members in this family, and therefore, I call this the octahedral plane. Okay. So, let me go down and pick up models to show you these 3 planes, which are important planes in a cubic lattice, and we will often deal with these kind of planes in the cubic lattice. Soumya has a question.
Sir, how do we determine that how many members are there in the family?
Okay. Exactly the same way we determine the members the way for family set of for the case of directions. We find all the symmetrically equivalent set of planes, and therefore, in other words, I take my plane, I apply all the symmetry operations of the crystal or the lattice and find out all the equivalent set.
So, it's the same as the direction.
Exactly the way you do it for directions. Okay. And for high symmetry ones, we saw that we could actually do a very simple what you call it mechanical way of doing it. We put all the negatives, we permute all the indices, suppose because this has to be a cubic system, therefore, the x axis is related to the y axis is related to the z axis. In other words, the a vector, the b vector and c vector are all related by the threefold direction, and therefore, I could just permute them and get all the possibilities and put negatives for all of them. Okay. So, let me choose this unit cube to demonstrate the 3 planes we have just considered. So, my 1 0 0 plane is nothing but any face of the cube. So, this is my face of the cube, this is a 1 0 0 plane, this is another 1 0 0 plane which is also the face of the cube, any one of them is a 1 0 0 member. Okay. Of course, the exact plane, is it a 1 0 0 or a 1 bar 0 0 or a 0 1 0, would depend on the origin and the orientation of the coordinate axis, but they all belong to the same family. So, these 3. Now, I am talking about a 1 1 0 plane. That means that it has intercepts, suppose this is my origin, this is my x axis, this is my y axis and the z axis. It has an intercept along 1 along the x axis, 1 along the y axis and infinity along the z axis. So, it will be a plane something like this, right. So, it will never intercept the z axis. So, you can see this. So, let me orient it a little different so that you can see this plane, and therefore, you will see that this plane goes to infinity along the z axis. Now, I have another model which actually puts this plane in perspective. So, you see here, this is a member of the 1 1 0 family. So, you can clearly see this is a perspex box within which I have drawn the 1 1 0 kind of a plane. So, you can see this plane. Now, let me draw the third plane which is the 1 1 1 plane. So, I have got a triangle. Again, I told you that all these planes are infinite planes, but I typically represent them by the section of that plane which lies within the unit cell, and that is why this looks triangular. Otherwise, all these planes would be infinite planes. So, so this is my origin as before. So, this 1 1 1 plane intersects the x axis along one point, that is 1 0 0, 0 1 0 and 0 0 1. Therefore, I can draw my plane as this plane which is here. So, this is an inclined plane which has intercepts along the 3 axes. So, I will just show it to you in different orientations, you can have a look. And as I mentioned before, this is a very, very important plane, especially when you are talking about cubic closed packed crystals. So, we will deal with this plane quite a bit when we are talking about the cubic closed packed crystals, and this, as we will see, will happen to be the closed packed plane in the cubic crystal, and in that case these directions will turn out to be the closed packed directions.
Sir?
Yeah,
Sir, can we find the edge planes in cubic lattice? Means the lattice which cuts the edge of the intercept. Means the edges, the intercept which cut the edges. Can you find the Miller indices in that edge?
Okay. Okay. I try to understand your question, and let me draw it on the board, and if I am wrong you can correct me. Suppose this is my cubic unit cell, and now I am talking about a cubic lattice. Can you come to the board and draw the plane which we are talking about? So, that I will give you a different colored chalk and then you can draw the plane. So, you are talking about a plane which is cutting the edges, right? So, we just draw the intercepts and I will draw this edge, and which other edge?
Sir, means any edges which cuts the plane.
Okay. So, just one edge, and where is the other intercept? It has to intercept.
Means any edge we can consider.
Okay. So, let me consider the simplest of the lot, assuming this is a cube now, and this is an important question. Okay. So, because I have only considered those planes, for instance, so far, which are at the faces. For instance, this would be a plane which I consider. Okay. Now, this is an alternate plane which does not pass through any of those and actually cuts the half point. Very good question. So, let me answer this question. Let me consider the simplest of the lot. Let me consider a translational equivalent plane of that. Okay. This is my plane now. Okay. And to make sure that this plane actually sits within the crystal, what I will have to do? I will have to draw the white line outside. So, in other words, if this were my origin, this point inside is my origin, and now my intercepts along, this is my x axis, this is my y axis, and this is my z axis. So, my intercepts for this plane along the x axis, it will be infinity, it will never intersect the x axis. Along the y axis, so I will write down my intercepts. The intercept along the y axis is half, because I have considered this at the middle of the edge for simplicity. It could of course reside anywhere in the edge, so I will write half for simplicity, and also it does not never intercepts the z axis. So, my intercept along the z axis would be infinity. So, now I go and find reciprocals of this. So, the reciprocal of this plane would become 0. So, this is my reciprocal. Become 0, 2, 0. So, Miller indices will become 0, 2, 0 if I like, or if I want to factor out the common factors, it will become 2, 0, 1, 0, and I can of course write it as 0, 1, 0. An important question arises, what is the difference between me writing it as 0, 2, 0 and the 0, 1, 0? They are, in other words, in some sense equivalent planes, but there is a subtle difference, and we will soon come that actually it is a very important question. That is why, because if you are talking about a set of 0, 2, 0 planes, that would include, for instance, these planes. So, suppose I call are equivalent to these planes. So, let me now label these planes. I call this plane 1, I call this red plane as 2, and just for sake of clarity, I will label this plane as 3. I will give them an orange color and label this plane as 3. These 3 planes are equivalent if I do not mention anything except this number 0, 1, 0, and I could consider any one of them as we already saw, but there is a subtle difference between these 3 planes, and what is that difference we will definitely consider after looking at the next slide. Okay. So, coming back to the main slides, so let me mention a few points about planes and directions before I return to solving that problem. Now, an unknown direction typically is written as u, v, w. Suppose I do not have a specific plane, I have an unknown plane, I will call it u, v, w. Sorry, an unknown direction I will call it u, v, w, an unknown plane I will call h, k, l. And suppose I am talking about a high index plane where I have double digit indices, I could separate them by commas. Of course, you could also use a space between the indices, but to be absolutely explicit, you can separate them by commas. A point which we will of course expound a little more in one of the coming slides is that in cubic lattices and crystals, the HKL plane is perpendicular to the HKL direction. Akruti has a question at this point.
HKL plane is perpendicular to HKL direction. Is it true only for cubic lattice or all the other?
Very good question. So, we will return to this question because we have a complete slide on this very aspect alone. So, we will return to this, and in the process we will consider another issue of what is known as the Weiss zone law. When you have a set of planes, I would also like to include what is known as the interplanar spacing, which is written as d subscript HKL, and I do not usually put the brackets on that HKL, the usual brackets, but I have to understand that I still mean the I am referring to the plane HKL within brackets. In other words, whenever I am writing DHKL, what I mean is DHKL. So, actually this is implicit that I am actually considering the Miller indices. So, what is the formula for DHKL for the cubic lattice? And as you can see, I have explicitly mentioned it is a cubic lattice, and the formula is A is the lattice parameter of the cube, and the formula for the interplanar spacing is A divided by square root of h square plus k square plus h square L square. Now, let me return to the problem in hand and try to calculate the interplanar spacing for the 2 kinds of planes we have just now seen. So, we have 2 planes here, the D110 and the other plane we have in consideration, which is nothing but either this one plane or the 3 plane, and I also have this red plane, which is the, as I calculated the indices, is D220, sorry. The plane here is D100 and the other plane is D200. So, given my formula, it is A by square root of 1 square plus 0 square plus 0 square, that is equal to A. In other words, the interplanar spacing is A if I write it as 100. We can clearly see, as far as the orientation goes, the red plane is no different from the white plane, the 1 or the 3 plane. So, D200 by this formula will be A by square root of 4 plus 0 plus 0, therefore, it is A by 2. In other words, the interplanar spacing of the 200 planes is half that of the 100 planes. Okay. Now, what does it mean? It means that the 100 planes is a subset of the 200 planes. If I consider a single plane, just a single one plane, of course I could position that plane here or here or here, and I would use an index like 100 for that plane. I could even place it somewhere in between. But when I am talking about real crystals, I would not arbitrarily place this plane, I would place it in the unit cell in a very specific way, and the specific way could be somewhere between the two, that is half along the y direction, or it could be 3/4 along the y direction, etc. Therefore, when I am considering a specific plane, I need to worry about what is this intercept. And the reason is that there could be atoms which could actually be sitting on these planes, which could actually be giving some diffraction or some other effect. Therefore, I need to worry about it. Now, what do I mean that the interplanar spacing of the 200 plane is half that of the 100 plane, and what do I mean also that this is 100 is a subset of the 200? I will explain here, and let me do it in one dimension for simplicity. So, these are my lattice points, say approximately equal. So, now what will be the, for instance, suppose this is just one dimension, therefore, I cannot have planes here, but let me just consider that this is a plane I am considering, and they will have only one index to describe that plane. So, this plane, this set of planes would be the white planes, and I call them the one set, and the index for this would be simply 1, right. Now, the other set of planes, which is here, let me draw the other set on superimposed on this top here. So, the other set of planes, which is now actually includes not only the planes which are between, but also the planes which are, so I will let me draw them now. The red planes are like 2, and I enclose it within brackets. So, the Miller indices of this plane would be 2. As you can clearly see that my red planes are located at 0, half, 1, 1.5, 2, 2.5, etc. But my white planes are located only at 1, 2, 3, 4, etc. That means that the red planes are a superset of the white planes. That means if I just delete half the red planes, I can get the white planes. So,
here there are a lot of planes. So, each planes are the subsets of everyone.
I am not very sure what you are asking, but let me explain the concept, go over the concept again of the subset and superset and the spacing. I have clearly seen that D200 has half the spacing of D100.
Yeah.
Now, question is, what is this D200 plane? It is not just this one red plane, but it is a series of red planes, because we understood now that when I am talking about DHKL, I am talking about the interplanar spacing. That means it is a spacing between all those set of planes. Okay. And now I am asking a question, that am I only considering these planes which are located in the front and in the back, which are like the 100 planes, or am I also taking into account planes which pervade at the middle. So, now I am talking about the 200 planes, I am talking about a plane in the middle, but also a plane in the corner. It is not that I have excluded these planes, these are now my 200 planes, this, right. And what is the interplanar spacing? It is half, right, half that if only my planes were located in this end and this end, right. So, this is my 100 set, as you can see. My 200 set has a plane in the middle also, right. Therefore, it has got half the interplanar spacing. Now, since this is the 200 set is not just this plane, it is this plane, this plane, this plane, all of them belong to the 200 set, and that is why my interplanar spacing is now this distance, right. Now, therefore, my 100 set only includes the 1 and the 3. So, let me write down the planes belong to the 100 set. It is the 1 plane in that diagram, the 2, 3 plane, etc. The 200 set actually includes the 1, the 2 and also the 3, right. So, therefore, it is a set which is half the spacing, and therefore, it is double in density of number of planes, right. Therefore, when I am like in the case of vectors in directions, I had said that if I am just worried about just the direction, then I can factor out all the common factors for the direction. But if I am worried about the length and the direction, then I cannot factor out the common factors. Similarly for planes, if I am not worried about what is the interplanar spacing or where that plane, I am just worried about the orientation, then I can factor out all the common factors, but I am also additionally worried about the interplanar spacing and their exact position within the unit cell, then I need to consider, I cannot factor out the 2, I have to keep the 2 within the numbers. So, this is an important point to note, and this becomes absolutely clear when, especially when we do the Bragg's equation to understand diffraction.
Sir, as there are two planes 100 and 200, then how we will confirm at the time of labeling that which is the superset and which is the subset, subgroup and which is the supergroup?
See, 200 is this plane, this plane, this plane, all of them are in the 200 plane. The 100 does not have the center. So, the 100 is contained within the 200, because now if I have my 200 set, I just drop this, I get the 100. So, this is the superset obviously. This has more number of entities, twice the number of entities compared to this.
So this is the things are, there is a lot of planes are there. So if we taken one fixed volume, so these volume sets are the supersets of another one, I think so.
Yeah, initial, we of course represent these planes only within the unit cell, but we have to always remember they are pervading entire space. They are a translational equivalent set or a set of planes which,
Yes.
okay, that is what it is. This also brings us to another point, perhaps not often discussed, is that I have 3 indices in 3 directions. As you know from the cosine law, that actually there is an equation connecting the 3 indices. That means the 2 independent indices would have sufficed in 3 dimensions. That means that when you use 3 index notation, as we are doing in Miller indices, there is some extra information that this third index is giving us. What is that extra information? This is the extra information, that actually embedded within my HKL planes is also the interplanar spacing. And that is why, even though I could suffice by writing in 2 index notation in 3 dimensions, because now I have an equation connecting the 3, which means that I can actually have a reduction in number of independent parameters, which would be 2 is sufficient, but I still insist on using 3 index notation in 3 dimensions because of the fact that I can actually calculate the DHKL, which is embedded within the information on the planes. So, let us now consider, as I told you, the 111 plane and try to elucidate some more properties of this 111 plane in cubic crystals. Now, when I talk about a 111 plane, for instance, in some sense, as I pointed out, the blue plane, the orange plane and the green plane are all 111 planes. But I have to take little care, especially suppose I am calculating the atomic density on this plane. I have to take certain care in choosing the appropriate plane, otherwise I may get a wrong atomic density. Suppose I was talking about a FCC crystal, a cubic closed pack crystal, and atoms were actually present on these planes, then, and in of course the cubic crystal, you will know there will be an FCC plane, there will be an atom here, an atom here, an atom here, atom here on this blue plane and so forth, because there are now atoms in the face centers apart from the vertices. I have to be careful in choosing my plane for making the calculations. In some sense, all these 3 have the same orientation, these 3 planes, but I have to be a little careful. So, let me calculate the D111 plane. So, these are all 111 planes. D111 is A by square root of 1 square plus 1 square plus 1 square, which is dA by root 3. I can write this also as A root 3 by 3, right. Now, what is A root 3? A root 3 or root 3A is the body diagonal of the cube. Now, what is A root 3 by 3? Is 1/3 of the body diagonal of the cube. In other words, my 111 planes will trisect the body diagonal. So, maybe that is shown in one of the slides coming up. Let me see, yeah, here. So, if I have a body diagonal of the cube, the 111 plane actually divides the body diagonal into 3 parts, and this is important because now that 111 plane which will actually trisect the body diagonal will be the blue plane and the green plane. So, that means the orange plane is truly not speaking belonging to the same set. It has got the same orientation, but I will not consider it when I am actually considering 111 planes. Because if I am talking about atoms lying on a 111 plane, I would only consider, for instance, the blue plane and the green plane to be equivalent and not the orange plane. And I have seen that the blue plane and the green plane together will trisect the body diagonal as given by the D111 information. Now, However, I may want to consider the orange plane because it is actually speaking the mid plane of this cube along the 111 direction. This mid plane of the cube actually breaks this this cube into two halves of the polyhedra, which are this polyhedra shaped here, and therefore I can get two halves, and if I want to do that operation, then I will have to consider the orange plane. Now talking about the atomic density, if I want to make a calculation of the atomic density, I have to be clear the kind of plane I have to choose has to be a space filling plane. In other words, those planes themselves should tessellate space in other words the content of the unit cell should, if extended in all the directions, should form the complete plane. Suppose I choose the central 111 plane, you can clearly see the central 111 plane was in the form of an hexagon. So, I have chosen different colors, but do not get confused. This blue color was the original orange color in this plane. So, this is in the shape of an hexagon, but you can see that if I extend it across unit cells, these hexagons themselves do not fill the entire two dimensional plane 111 kind of a plane. That means that I have to add additional triangles to make the complete space filling. Therefore, if I make my atomic density calculation or one of those calculations based on this kind of a blue 111 plane which is shown as a hexagon here, I will get my number wrong. So, this point has to be kept in mind that I have to also additionally worry that which plane in the unit cell I have to choose, and clearly the correct choice for this cubic crystal system would be the blue plane or the green plane. And suppose I am talking about division of this polyhedra then into a mid plane, then this orange plane is the mid plane which actually bisects my body diagonal. I was mentioning about a family of directions, and I was also trying to relate it to a concept of the, for instance, I call the 111 plane the octahedral planes. Okay. The 111 plane is an octahedral plane for the cubic lattice, and as I mentioned, it has got the highest symmetry, and therefore there are 8 members. Now, therefore, I can think of these 111 planes, all the equivalent set of 111 planes, which will include planes like 111, 1 bar, 1 bar, 1 bar, 1 bar, 1 1, 1 1 bar 1, and so forth. There are 8 members in this family, and those are the 8 members which are shown in this diagram. In other words, it is in the shape of an octahedron. So, I can actually understand it by taking a cube and trying to put the octahedral planes. So, this octahedron should reside within the cube. So, let me break the cube a little bit to get the octahedron inside. So, I will see that these planes, because they, if exactly this octahedron had fitted within the cube, then these will be my octahedral planes. So, you can clearly see this is, so these are the 111 planes. Okay. They are in this case, of course, I am just considering the orientation, I am not considering the exact position of the 111 planes, but I have to remember the whole family of these 111 planes form an octahedron like this, and all these are these triangular faces, and therefore they are octahedral planes. If I have to truly represent these octahedral planes, I will have to go outside the unit cell and look at the way I have done it in this diagram, wherein 8 unit cells, each one of them having one of the members of the family is shown, therefore forming an octahedral plane. Now, as I mentioned, the family of planes is a symmetrically related set. It could so happen that the cubic crystal I am talking about actually has only 2-3 symmetry. That now suppose I am talking about a cubic crystal with 2-3 point group symmetry. That means it has a lower symmetry than the and this is nothing but the tetrahedral symmetry. Then in such a crystal, there will be only 4 members in this family which will form a tetrahedron, and you can see the 4 members of that family inscribed within a tetrahedron. So, you can see here that there are 4 members of this 111 family which go inside the cube and they form a tetrahedron. So, let me show this tetrahedron which is inscribed, or of course, here I will not inscribe it, but I will show you the relative orientation within the cube. The way to construct this tetrahedron within the cube is to consider one phase diagonal which is on one direction, the other phase diagonal which is perpendicular to it. So, I can inscribe a tetrahedron within a cube. Of course, in this case I am not inscribing it, I am just merely positioning it. So, you can see that by doing that I can actually see where is the orientation of the planes with respect to the cube. You can see that. So, this is my tetrahedron, and now clearly this crystal, since has only tetrahedral symmetry, it has got only 2 3-fold axes, which is this one 3-fold and this second 3-fold and third 3-fold, and such a crystal clearly does not have any 4-fold axis. Okay. Therefore, it is important to understand that this 111 plane has very important role in many kinds of crystals, even of lower symmetry. And typically, if you are talking about FCC crystals or simple BCC crystals, this will be an 111 plane will be an octahedral plane having 8 members. So, let me write down a list of various indices of the cubic lattice or a crystal, for instance, and write down the number of members in the family. The 100 has 6 members, which nothing but forms the faces of the cube. It is the simplest. Okay. The 110 has 12 members, and we can see that the 110 plane actually bisects the face diagonal. The 111 member has 8 members, and the 111 planes actually trisect the body diagonal. You go to higher index planes like 210, 211, 311 or 321, you will see that the number of such members actually increases from 12 to 24, then you can go to 48 members this plane. This has so many members because now, so the 321 plane has 48 members in the family, and that is the maximum any member in the cubic lattice can have, because now all 3 indices are different. You can permute all the 3 indices, and that will lead to 3 factorial ways. You can make them negatives, and therefore you will end up with 48 distinct members in this family, the largest family. Sometimes if you are looking at certain older texts or certain journal papers, you might come across certain alternate notations for family of planes or directions. So, this is just a summary of them, but more often than not we will stick to the kind of notation we have been using. So, for direction, this is a single member, this is a family. Sometimes an alternate symbol for a family like this is also used. Single member for a plane is like this, and for a family is below that. Sometimes a double bracket is also used for a family of planes. Additionally, they may also use a concept for a point and for a family of points, like you could have a point xyz which is put within dots, and a family of those points now which will be a symmetrically related set of points as between a symbol which looks like a colon. So, certain all these symbols may be useful when especially reading journal papers. Briefly we will go over this topic of certain points about the HKL planes, and maybe this may not be at this point of time very interesting, but it is worthwhile to note these points. If you have a translationally equivalent set of lattice plane that will divide, for instance, the cell edge, the A edge, it will along the 100 direction, if you have an HKL plane, will divide into H parts. Along the 010 direction, which is the B direction, the HKL plane is divided into K parts. Along the C direction, it will divide into L parts. Now, this is the cell edge divisions. Suppose you are talking about how the diagonal or the face diagonal which is divided along the HKL plane, for instance, will divide the 011 direction into K plus L parts, the 110 in L plus H parts, and the 001 into H plus K parts. The body diagonal is divided into H plus K plus L parts. In other words, for the 111 plane, suppose the body diagonal will be divided into 3 parts, 1 plus 1 plus 1, 3. So, let me take up an example to show you what happens. Suppose I am talking about the 111 plane, then my face diagonal is divided into 1 plus 1, 2 parts. If I am talking about edge, it is just divided into 1 part, right. So, this whole thing remains 1 part. Okay. So, then the body diagonal is divided into H plus K plus L parts, right. So, therefore, we can get some more useful information in terms of the division of the edge, the face diagonal, and also the body diagonal from the HKL index. Additionally, you will notice if that H is even, then it will pass through the midpoint of A. If H plus K plus L is even, it will pass through the HKL plane will pass through the face center of 001, and H plus K plus L is even, it will pass through the body center or the midpoint of the body diagonal. So, we have to note there are additional information we can obtain from understanding these Miller indices, though at this point of time I am just briefly mentioning it, I am not going into the details of this analysis. Instead, I will take up the next important topic, which is the concept of Miller-Bravais indices, which is specially used for hexagonal lattices and hexagonal crystals. Now, the Miller-Bravais indices is on the same kind of footing as the Miller indices, but has an additional index which has been put in to describe these hexagonal lattices and crystals. So, it is a 4 index notation. The important point to note in this 4 index notation is that the first 3 indices are symmetrically related set of on the basal plane. So, we will see what is the basal plane, and we will see that the first 3 indices which are related to the A1, A2 and A3 direction all lie on this basal plane, and they are symmetrically related by the 120-degree rotation, which is a symmetry operation of all hexagonal lattices. The third index is a redundant one, and why is it redundant? Because we know that in 2 dimensions, which is now the plane I am talking about, the basal plane of the hexagonal lattice for instance. So, let me pick up the hexagonal lattice. So, I am a hexagonal lattice in blue color here. So, I am talking about this plane which I call the basal plane. Additionally, later on we will see that I will also define other kind of planes. So, this is my basal plane, either the top plane or the bottom plane, I call them the basal plane. I will call them these planes as prism planes, and planes which are inclined as pyramidal planes, the planes which are inclined like this, they are called pyramidal planes. Now, when I am talking about a basal plane, I am going to define 3 vectors. So, these 3 vectors 1, 2, sorry. So, I have these 1, 2, 3 vectors all lying on this plane, and what I am trying to tell here is that one of these indices is redundant, because we know in 2 dimensions we need just 2 indices to describe a lattice or a crystal, and the third index obviously has to be redundant. What is the reason that we include such a redundant index? This is introduced to make sure that the members of a family of directions or planes have a set of numbers which are identical. I will explain this concept by taking examples, but what I am trying to say here, in other words, I should be able to permute the 3 indices and get all the symmetrically related set of directions or planes, like we did for the cubic lattice for instance. If I have for instance 1, 1, 0 plane, then I can actually, because these now for a cubic lattice the first index, second index and third index are all equivalent, I can actually permute them. So, as I can, by merely looking at a 1, 1, 0 plane and a 1, 0, 1 plane, I know they are identical kind of planes as far as the lattice goes. I should be able to do a similar kind of thing, and I can do only that if I have this redundant index. The fourth index is along the C axis. Now, suppose this is my hexagonal, the fourth index, the C index is along this. So, it is the direction which is the vertical direction in this cube. So, whenever I am dealing with hexagonal lattices or crystals, I can permute the first 3 indices to get the distinct members of the family, and the fourth index is kept separate. We have to remember the fourth index is separate crystallographically as compared to the first 3 indices in the Miller-Bravais notation. So, I have the A1 direction, the A2 direction and the A3 direction all lying within the basal plane. They are all related by the 120-degree rotation, the 6-fold rotation which hexagonal lattices have, and therefore, they can be permuted. So, the H index is related to the A1 direction, the K index is related to the A2 direction, and the I index is related to the A3 direction, and the L index is which is a separate one, is related to the C direction, which is perpendicular to the basal plane. So, let us now try to generate some planes and try to derive their Miller-Bravais indices, and these examples will also make it absolutely clear that why we need a 4 index notation and what is the concept of redundancy. Now, for instance, this is my plane in projection, the blue plane, and in proper orientation you can see this blue kind of plane. So, let me show this in the figure also. So, this is my hexagonal kind of unit cell. So, I am considering a plane which is now passing through. So, let me use this orientation to make it clear. So, this is my plane. Right. So, it actually is like the diagonal of the basal unit cell, the prism rhombus unit cell which has been extended upward. Now, I will try to derive the Miller indices. So, I start Miller-Bravais indices. So, I start with my intercepts. So, intercept along the A1 direction is 1, the intercept along the A2 direction is 1, Now I have an additional redundant index A3 and my intercept along the A3 direction. So, the A3 direction is in this direction. So, it is along minus A3 and it is half the distance. So, at this point is minus half. So, it is 1 1 minus half, and along the C direction it is infinity, it never intercepts the C direction. As before, to get my Miller-Bravais indices, I will take reciprocals of these, and these are now 1 1 2 bar 0. First of course, I will write it as 1 1 minus 2 0, then as you know in Miller indices and Miller-Bravais indices, as in this case, I would not leave the negative outside, but I will put it as a bar. So, the indices for this plane would be 1 1 2 bar 0. Now, I will take one more example before we understand the concept of this fourth index. Now, suppose I have two planes, the blue plane and the green plane as shown in this cube. It is absolutely clear as far as the hexagonal lattice goes, they are equivalent planes, they are related by the symmetry operations of the hexagonal lattice. Therefore, if I look at the indices of these two planes, they should look identical to me, so that I am not confused that I am not talking about different kinds of planes, right. So, now what are the indices of this blue plane and what are the indices of the green plane? Let me start with the green plane. Intercept along the A1 direction is 1, the A2 direction is minus 1, because the A2 direction is in this direction, it is minus 1. The intercept along the A3 direction is infinity, it never intercepts, this green plane never intercepts the A3 direction, it is infinity. Obviously, the intercept along the C direction is, as you can look from this green plane, along the C direction also it never intercepts the C direction, therefore, I write it as infinity. To make the Miller-Bravais indices, I make the reciprocal. So, I will write it as 1 1 bar 0 0, both the infinities become 0, and therefore, they are as before. I could have put this green plane passing through the origin, that means I could have drawn the green plane like this plane here. So, it as if it were a plane passing through the origin, and I do not do that for the same reason I mentioned for the normal Miller indices, that I will land up with infinities when I take reciprocals. So, I will always translate it so that it is 1 unit away from the origin. So, I have 1 1 bar 0 0, right. Suppose I were not using a 4 index notation, I were using just a 3 index notation, that means I do not have this third index which is a redundant, I do not have this third index redundant, then I will write as 1 1 bar 0, right. Now, let me look at the blue plane and try to derive its Miller-Bravais indices. Its intercepts along the A1 direction is infinity, it never intercepts the A1 direction, it is parallel to the A1 direction. It intercepts the A2 direction at a distance 1 1, it intercepts the A3 direction at a distance minus 1. So, this is A3 is positive A3, this is negative A3 at minus 1 intercept. So, this is my point along intersection along A3. So, I have infinity 1 minus 1 infinity, as usual the C direction it never intercepts. My Miller indices or the Miller-Bravais indices would be 0, I take my reciprocals, this becomes 0, this becomes 1, this becomes minus 1, which I write as 1 bar, and this is 0. So, my Miller-Bravais index is 0 1 1 bar 0, but suppose I were using just 3 index notation, the Miller indices, that means I do not have my third index here, this would be 0 1 0, right. Clearly, the green plane and the blue plane as far as the lattice goes are identical. In other words, I can use a 6-fold rotation which will take me blue plane to this plane which I have not shaded here, and then it will take it to this green plane. So, let me show these planes in a model. So, one of my planes was this plane, the other plane was a plane like this. So, this was my say the green plane, this was my blue plane. So, this plane is rotated by a 6-fold to this plane, which is rotated by a 6-fold to this plane. So, all these planes are identical as far as the lattice goes. Now, and therefore, my Miller indices should reflect that symmetry. But looking at the Miller indices in 3 index notation, the first plane would be called 1 1 bar 0, second the blue plane would be 0 1 0. Clearly, even though they are equivalent, the Miller indices seem non-equivalent. To avoid this kind of ambiguity, and therefore, now my question is that how do I generate my family, right, given the highest symmetry for the hexagonal lattice, which is therefore, to avoid that ambiguity, I will write a 4 index notation, and in the 4 index notation it is 1 1 bar 0 0, and this is 2 1 1 bar 0. Keeping the L index separate, I can clearly see there is 1 2, there is 1 a 1 bar and a 0, and there is a 1 and a 1 bar and a 0 in both indices. So, using a 4 index Miller-Bravais notation, where in the first 3 indices are referring to the basal plane, which is the plane, this plane shown here, I will actually see that I will bring out equivalence between equivalent planes. So, this is why the additional index is there, and now I can go ahead and permute and generate all the equivalent set of planes. For instance, now I want to generate this equivalent set. For instance, I want to write this plane or one of these planes. There will be, for instance, there will be 1 0 1 bar 0 or 0 1 bar 1 0. So, they are all by merely permuting the first 3 indices, I can get all the equivalent planes. That is why we have the utility of the Miller-Bravais indices, wherein we include the ith index. Now, we said that the ith index is related to the so, the ith index is related to the remaining 2 index, that is why it is redundant. I can derive my ith index as minus h plus k. So, in this case, for instance, it is minus 1 plus 1, which is 2 bar. In this case, my ith index, the third index, is minus of 1 plus 1 minus 1, which is 0, therefore, this is 0. Therefore, I can derive the third index from the first 2 indices.
So, why not here 1 bar and you taken just 1?
Which one?
Just before here, Miller indices you indicate 0 1 1 instead of 0 1 1 bar 0.
Which one? Which plane?
For right hand side planes.
This one?
Yeah.
Oh.
So, here you taken 0 1 1 bar 0
Oh.
and just before it you ignored 1 bar and just taken 0.
Yeah. So, this is the 3 index notation, which is called the Miller indices notation, wherein I do not have my A3. So, in other words, I will only talk about A1 and A2, which should have been sufficient, because in the Miller indices we have only 3 index notation, and for 3 dimensions 3 index notation is more than sufficient. We just introduce an additional redundant index to make things very clear. So, it is always, even if you write it here, the third index always exists, which is nothing but minus of 0 plus 1, which is 1 bar, which I write as 1 bar. So, to make it absolutely clear, I index additional index I, which is a redundant index. Good question, but this is why the whole purpose of introducing a redundant index. Now, let me consider one more plane, and you can see again we are considering a green plane and a blue plane, which are identical, to illustrate the concept of Miller-Bravais indices. For the green plane, so the intercepts are 1, in this direction A2 direction is minus 2, and in the A3 direction again it is, we are not showing the intercept, it will go and intercept at minus 2. The intercepts are 1, minus 2, infinity, because the C direction it does never intercepts. The intercepts for the blue plane are 1 along the A1 direction, 1 along the A2 direction, and minus half as before along the A3 direction infinity. So, I can derive the Miller indices from the intercepts as reciprocals 2, 1 bar, 1. So, actually it will become 1, half bar 0, and I will multiply throughout by 2. In other words, I will take the half factor outside, it will become 2, 1 bar 0. For this plane, it will become reciprocal, this will become 1 1 2 bar 0, and that is what it is, 1 1 2 bar 0. And since these are equivalent planes, as obvious from the figure right on the right hand corner, you can see the equivalence straight away by looking at the Miller-Bravais indices. So, this has got a 1 1 2 and 2 1s in the first 3 indices and a 0 of course for the last, and here it has got again a 1 2 bar and 1 1. As far as the negatives goes, in other words, suppose I want to actually see the equivalence, I may have to multiply this by minus 1, and that can be done because now we are not distinguishing planes on other side of the origin. Suppose a plane had HKL, in other words, I am looking at a specific plane HKL, and now I am not worried about the whole set of those planes HKL. The HKL plane will lie on the positive side of the origin, while an H bar, K bar, L bar plane would lie on the other side of the origin. But if I am talking about a set, then I do not distinguish these two planes. So, let me also consider some examples of pyramidal planes. For instance, this pyramidal plane, in other words, wherein the C index is what you might call finite and not the C intercept is not infinity. So, let me take this blue example. So, the intercept for this plane along the A1 direction is 1, along the A2 direction is 1, along the C direction it is, sorry, this is again 1 actually. Sorry, the A3 direction is the one direction which I am talking about, the third direction is minus half. In other words, this is my intercept here, A3 direction is minus half, and along the C direction it is 1. So, let me switch to my highlighter. Okay. Now, So, my intercepts are 1 1 along A1 and A2, 1 along the C direction, and the redundant intercept is here, which is minus half. So, I can write down the Miller indices of this plane as 1 1 2 bar 1. So, let me consider this plane which is shown here, and so in the right hand diagram and the left hand diagram it is exactly the same plane. Only thing I have done the different is that I have only marked the part of the plane which lies in the unit cell, and here I have marked the part of the unit which lies within the complete hexagonal representation which we normally choose to reflect the hexagonal symmetry. So, the intercept for these planes are along A1 direction 1, along the A2 direction it never intercepts, that means it is infinity, along the A3 direction it is minus 1 which is along this direction, and finally along the C direction it is 1. So, I take my reciprocal and put brackets to get the Miller-Bravais indices, which becomes 1 0 1 bar 1. So, this is my Miller-Bravais indices for the plane, and therefore, I can clearly see that I can use a 4 index notation in the case of hexagonal crystals and hexagonal lattices to derive the Miller-Bravais indices.